All right, in this video, we'll cover kinetics of nuclear reactions or nuclear decay. And what's nice is that this is all first order. So nuclear kinetics, always going to be first order. So there's a couple equations that we'll revisit from I guess the beginning of the quarter, and they're all going to pertain to first order. So for example, half-life is, if you remember, natural log of 2 over k, or you can write it as 0.693, which is what the natural log of 2 is, abbreviated, over k. So if we use this in this problem to solve for our rate constant from our half-life, the only thing is the units, so they want the rate constant in seconds to the -1, or 1 over seconds. So we'll need to convert our half-life into seconds. So if I solve this expression for k, just becomes natural log of 2 over the half-life. Or again, you can write 0.693 instead of ln 2. So here I'm going to take this, just do some dimensional analysis. So we have 24 hours per day and 3,600 seconds per hour. That's just 60 minutes times 60 seconds per minute. And that gives it would be ln of 2 over basically 1.11 times 10 to the 6th seconds. So our k is about 6.24 times 10 to the -7 seconds to the -1. Right. Part B, we have a sample containing 28 milligrams of this copper-64 isotope. How many decay events will be produced in the first second? So if you remember first order, basically the rate law looks something like this, right? Where you just have the concentration of your reactant to the first order, first power. So that's how it's going to work. Sometimes, you can use like a capital N for the nucleus or nuclei, so it's kind of like that. And when we're doing specifically with nuclear reactions and these decay events, this is also what's known as the activity. The nuclear activity, which is just essentially how many nuclei are decaying. And just from a conventional unit standpoint, they like to use seconds as the time unit. So how many nuclei are decaying every second, essentially. So keep on against the same equation, basically, and what you want to use here is not a molarity like we kind of do normally with kinetics. This is actually the number of nuclei or number of atoms. So it doesn't really matter which unit you use here, same thing. And so therefore, what we're going to need to do is figure that out. So we're going to have 28 milligrams of this copper-64. We can then figure out the number just from, again, some dimensional analysis, converting to moles. Since this is a particular isotope, it has a mass of just 64. It's not like a sample of copper, which is an average of different isotopes. That's what you would use the periodic table for if it was kind of normal elemental copper. And then we have Avogadro's number that we're going to want to use, because again, we want to get nuclei or atoms as our final unit here. So we have 2.63 times 10 to the 20 nuclei or atoms. in our 28 milligrams of this copper 64. So therefore the rate would be, again, K times that, K from our part A, 6.24 times 10 to the negative 7, and then we multiply by this, and we get that there's about 1.6 times 10 to the 14 nuclear decays per second. So you can kind of write it as nuclei per second, or sometimes the way it's referred to is decays per second. Again, it's just how many nuclei are falling apart, basically. And again, that's the same thing as the activity. And there are other units like the Curie and the Becquerel. You can look them up, or if you have, Alex's topic, they probably will give you the conversion. But basically, you just convert with some ratio into those other weird units if they want them. But the way you do the problem is the same. All right, so the last part is just a typical kind of kinetics question where, normally with an integrated rate law, you are using this form to figure out like how much is left after a certain time or how long it takes for something to be used up. So if you remember for first order, it's the natural log form of this, reactant and negative KT plus the natural log of the initial amount, which again, you can kind of put in different forms depending on what you're solving for. If you're solving for time, this is sometimes an easier way to approach it. You also have like this form if you're maybe solving for how much is left or your ratio or something. So a couple different ways to arrange this first order rate law. So there's actually a longer way and then a really quick way to do this problem. But just to kind of go through, let's say we were like, solving it with this thing, then we want to know basically if the reactivity, needs to be at least 25% of the initial amount. So what we can say is that A over A naught is 0.25, 25 over 100. And then so this is our final of our initial amount. And then we have our K from, again, the beginning. And then our T. So then we just rearrange this for time. And that would be time in seconds, which would be like 2.22 times 10 to the 6 seconds. So then you would have to, again, use your conversions. And basically, if you convert that, well, you don't have to. I guess this could be your answer. But if you convert that into days, this is kind of where this is going. That would be 25.6 days. Okay, so this is again is a longer way. So there's a shorter way to do it. Is just use the half-life. So we know from part A that the half-life is 12.8 days. First order half-lives are going to be constant. They don't vary depending on how much you have. It's always the same amount. So if you start off with 100% of your sample or reactant, after one half-life, you're going to have 50% left. Remember, after another half-life, you're going to have how much? 25% left. So this is just 2 half-lives, right? And that's how we get that. So quick way, if it's again something like half of it left, 25% of it left, 12.5% left, something that's an easy multiple of the half-life. We can just use that concept. Okay, so hopefully that makes sense. For this one, also a book problem, we have a problem where we're determining how old a rock is. So there's like carbon dating, you're determining from carbon-14 how old something is, like maybe a piece of clothing that was found in some archaeological dig. In geology, oftentimes different, like really long-lived isotopes like uranium. So we have this uranium isotope, here's the half-life, we're gonna need this. This is gonna allow us to figure out how old this rock is. And what's happening is that the uranium-238 is decaying into lead-206 by a series of events that we don't really need to know, but kind of like reactant product. And all we know if we analyze this rock is how much of these isotopes are remaining at this point in time. So we're going backwards. If we're kind of constructing like a before and after, or like an initial kind of final table, then what we are basically given are like these final amounts of these two. And as it says in the problem, what we're going to assume is that the initial amount of the lead is 0. It just starts with, this uranium is what's producing the lead. So the lead is made from that. So we're going to have to figure this out. We don't know this initial amount. And then the thing that you don't want to do is, let's say, like plug in like 1 milligram for here, because we want to use an equivalent unit, like number of nuclei, or moles is either one, but something that you can use to keep these consistent in terms of this table, right? Because a gram of uranium is not the same as a gram of lead, different molar masses. So basically, we're going to do first just a mole conversion, and that would look like this. Let's see, so 1 milligram of uranium, so we can convert to grams. What's nice is that you just want to use the specific mass of that isotope. So 4.2 times 10 to the negative 6 moles of the uranium. So it's going to go here. So again, when you're converting the masses into moles, you have to use the molar mass of that particular isotope. So for the lead, it's going to be 206, right? You don't want to use the number on the periodic table, which is an average of different isotopes. So this is going to be 3.34 times 10 to the negative 6 moles of lead. So that would be, again, our final number here. Okay, so then thinking about this problem, it's just always 1-to-1, which is nice for nuclear reactions. So we have kind of like, this idea. And then we could obviously figure out what X is because of the lead number. So our initial amount of uranium would just be the final amount plus the amount of lead. So I'll say that again. The initial amount of uranium that we're going to find is our final amount of uranium, the 4.2 number, plus the 3.34, because that's what was used up to create the lead in a 1-to-1 manner. So our initial uranium-238 is going to be 4.2 times 10 to the negative 6 moles plus this many moles. So that's going to be 7.54 times 10 to the negative 6 moles. Okay. So then what we can we have that number, we can just use our integrated rate law, right? This will be basically our final amount. This will be our initial amount. And then we're going to use just something like this to figure out, first order, right? Figure out time it took in order for this to happen. So before we plug these things in, last thing will be to figure out the K. As usual, they just give us the half-life. So that will allow us to find K from that. So find K. Okay, so we have T1/2 natural log of 2 over K. So K is going to be ln2 over the half-life, which is 4.5 times 10 to the 9th years. We'll just keep it in years. This gives a rate constant 1.54, 10 to the negative 10 years to the negative 1. So there's our K value. And then we can plug it into our rate constant. Okay, so we can plug this into the rate law, which I'll just write in this way. And then we can solve for our time. Should be ln final over initial and divided by negative K. So we have ln our final amount, 4.2 times 10 to the negative 6. And our initial was 7.54. So you could cancel out the 10 and negative 6 if you want. And then we have negative K down here. This will be in years the negative 1. So we should get an answer in years, which is 3.8 times 10 to the 9th. 3.8 billion years old. So if you've ever wondered, that's how they do that, how old these rocks are. Also, just from a concept like checking your answer, if you think about the half-life is 4.5 billion. So this makes sense because if you look at the amounts, I guess I didn't write it up there. From our initial to our final, we haven't used up half of it yet. I guess we can see it down here. So that makes sense that we haven't quite got to the first half-life, although it's kind of close. But again, just ways you can use that idea to kind of check to see if your answer is in the right range. So hope that makes sense, and keep doing your problems, and best of luck.